Normally in a class like this, at this point, I'd sit back and put this first slide up and I would be like, describe what a desert looks like to me. And a lot of people would tell me about the palm trees and the big sweeping sand dunes and Bedouins and maybe throw in some camels. But it's a little bit different teaching this class here in Mesa because that's not what a desert looks like, and most everybody's just like, you look out the door, right? And I haven't seen a sand dune wandering its way through Mesa in a while, so I think our idea of a desert is a little bit different than the reality of many of them. So, what exactly is a desert? Well, it's a region that's so arid or so dry that it only has vegetation covering less than 15% of the surface. Um, so we can define it based on vegetation alone. And a lot of times we define it by rain as well. Anything less than 9 inches of rain a year is considered arid or a desert. What's interesting here is because of the lack of water, there are no permanent streams in deserts except for the water that comes from somewhere outside of the desert. So think of like the Colorado going through Arizona, that water starting up in the Rocky Mountains. Or think of the Nile flowing through the Sahara Desert. That water in the Nile definitely didn't come from the Sahara Desert area. It was carried from somewhere else. So what causes deserts? If you look at this map, it shows you all the major desert lands within actually the whole world pretty much. So you can see we are over here in the Sonoran Desert, but that means we're very close to the Mojave and the Great Basin, and the Chihuahuan Desert that stretches down to Texas. Other ones you've probably heard of are the Atacama, or the Sahara, the Arabian Desert, the Great Indian Desert, the Gobi, or the Simpson and Great Sandy Desert, or the Kalahari, or the Namib Desert. So deserts are caused by a number of different things. So let's look at a few of those. The first type of desert is called a subtropical desert. These form because the regional pattern of air circulation in the atmosphere. So if you look at the equator, it's called the equatorial low. The air that's right along the equator is heated up at the surface, and hot air, this is important, hot air holds more water than cold air. So as it gets heated up, it's able to evaporate a whole lot of water out of the oceans there. And then that hot moist air starts to rise. And when it gets up to the upper part of the atmosphere, it gets cold. And when it gets up there and it's cold, it can't hold as much water. And so that water is released as rain. And that's why the equator is so nice and green. It's because it rains a lot there as the air is rising. But what happens is once it gets cold and releases all its water, it's really dry. So it spreads out and it ends up sinking back down at about 20 to 30 degrees north and south of the equator. And these are the subtropical highs. It's called high pressure because the air is pushing down at the surface there, so the air pressure is higher. That dry air heats up, and then it wants to start sucking up water too because now it can hold more water. So you have really high evaporation rates there, but you unfortunately don't get the same rain that you do. And so that ends up being really, really dry. So some examples of these subtropical deserts include the Sahara, or the Arabian Desert, the Kalahari, and the Australian deserts. Those are going to be the places you're going to find those subtropical highs. Now there's another type of desert called a rain shadow desert. These can be a little bit smaller. Airflow from the sea or the ocean moves towards mountain ranges along a coast. And as they hit the windward side of the mountains, that nice warm ocean water starts to rise because it gets forced up and over the mountains. And as it rises, it cools off. And as it cools off, it starts to rain. So you actually end up getting like even rainforest along the coast. But now is once that air actually makes the leeward side of the mountains or the side away from the wind, it's already lost all of its water or its moisture, and it's actually very, very dry back there. I've got a really cool example. We can go up to the state of Washington. Now, let's say I tell you I'm going to go on a trip to Washington. And I'm like, what should I pack? What clothes should I bring with me? A lot of people are like, bring a jacket, maybe an umbrella, because our idea of the weather in Washington is very much based around like Seattle. And Seattle gets quite a bit of rain. If we look, it gets somewhere between 40 and 60 inches of rain a year. Um, so as air is blowing into Washington off of the Pacific Ocean, the first thing it does is it hits those mountains right along the coast, the Olympic Mountains, and it starts losing water and it starts getting rain there. There are actually places in the Olympics that get over 180 inches of rain a year. It's actually a temperate rainforest right along the coastline there. So then it drops back down and it goes through the valley where Seattle is, and it's still got a little bit of rain. But then as it passes over Seattle, it goes into the Cascade Range, and the Cascades are really, really tall. And so they ended up using up whatever moisture is left. And so as you can see in the map, in the Seattle area, there's 40 to 60 inches of rain a year. But as we get all the way over there, just east of the Cascade Range, there are places that get less than an inch of rain a year in Washington. And so their climate is actually rain-wise very similar to what we have here in Mesa versus like the nice rainy area in Seattle. At least Washington's not quite as hot. They're just dry. Now, another cause of deserts is what's called a coastal desert. Coastal deserts form when you have cold ocean water that cools the air above it. And of course, that cold air is now dry. So when it gets blown on land, that really dry air has no moisture, so it's not going to rain. And since it's so dry and it's kind of going on to warmer places, as it warms up, it wants to suck up more moisture, so it starts evaporating really, really heavily. And those higher evaporation rates tend to make things even drier. So the best example of this is the Atacama Desert. The Atacama Desert is actually really interesting. It has the unique distinction of being the driest place on Earth. The average rainfall for the entire Atacama Desert is 15 millimeters, which isn't much at all. Now, of course, it varies across there. There are some places that can get up to, they can get more, and there's places that can get less because there's some areas that have never actually had any measurable rain at all. Now, something kind of cool happened a couple years ago. In 2015, they had some serious floods in the Atacama Desert. They showed record-setting rains. It caused flash floodings and mudslides through the entire region, though, and it killed 28 people. On one day in March, a city called Antofagasta, Chile, actually received 23 millimeters of rain that day. Now, that's 0.9 inches of rain, but that accounts for 7 years of precipitation. And it turned the whole town into a river of mud, and it actually was a pretty big mess just getting that 1 inch of rain. So we tend to think of Phoenix is a desert, but it is nothing like the Atacama. You can also form deserts in the interior of continents. And this is because air masses that are moving across a continent are going to be losing moisture as they go. They're going to be raining or snowing as it goes. So by the time they get to the interior of the continent, there's really no water left. And this Gobi is the largest example of one of these on Earth. One of my favorite types of desert, though, are the polar deserts, because we don't think of the poles of Earth, so North Pole, South Pole, we don't think of those being particularly dry. But interestingly enough, they really are. Polar deserts are dry in part because it's an area of subtropical high pressures, just like we saw um, at the very beginning of the types of deserts, but also in part because of cold ocean currents that are just offshore. So it's kind of gets a double whammy. Antarctica is the largest by far. The average precipitation for the entire continent of Antarctica is only 6.5 inches of rain a year. That's about what we get here, but it's a big continent, so it ranges from as high as 25 inches to as low as only 2 inches of precipitation in some locations. And that's what you're seeing here in the pictures. On the left is the dry valleys of Antarctica. That's actually where they do Mars polar research because Mars is really, really cold and really, really dry, and so is this particular region of Antarctica. So if we look at weathering processes really quick, here's an important question. What are the conditions that speed up chemical weathering? Well, chemical weathering occurs the fastest when it's warm and it's humid or wet. So in a desert, it's going to happen really, really slowly. That means our dominant weathering process is going to be physical weathering. But we do get some interesting examples of chemical weathering in the desert. These pictures you see down here on the right is the White House ruins from Canyon de Chelly. And if you've never been to Canyon de Chelly, I highly, highly suggest it. But you see that black that's across the sandstone there? That's coming down from the top of the cliff. That's called desert varnish. So this is a thin, dark coating of iron and manganese oxides on the surface of rocks. This only happens in the desert. It's a sort of a reaction between wind-blown clays that get blown in like dust storms and iron and manganese that are in the rocks. Plus, there are microorganisms that actually live on the surface of the rocks, and they help pull the iron and manganese out of the rocks and leave behind this really thin coating. So the desert tends to be sort of dark in a lot of places because of this. You can see, I mean, it looks black on that cliff, but it's really pretty kind of buff-colored sandstone behind it. The picture on the left is actually from the white tanks, and you can see those are petroglyphs. Now, the white tanks are made out of a really, really white granite. Except you never know that just looking at this rock because it's black. But what the native peoples that lived here figured out is if they took another rock or something else and they carefully whacked it on that desert varnish, they could chip it off. And when you chipped away the desert varnish, it exposes that light colored rock behind it. So a lot of petroglyphs are created in desert varnish. It's also one of the ways they figure out how old they are is based on how quickly desert varnish develops. Now, while I'm talking about weathering and erosion, I need to make sure and point out there's one dominant process in erosion in the deserts. That's running water. Now it seems a little weird, right? Because you're like, well, it's a desert, it's dry. But if you think about it around here, it is dry most of the times. But when we do get water, we get massive flash floods. The water moves through very quickly and it can have a lot of erosional work. And we can see this because we have lots of these dry streams around, and these dry streams actually run with water when it's wet. But oftentimes they're just channels that are completely dry, and these are known as arroyos, at least in the Southwest for the most part. If you were to travel to the Middle East, because they have a lot of deserts, a lot of our desert terms are Arabic in nature just because the Arabian Peninsula is a big desert. So if you were over there, they refer to these as wadis, it's kind of a fun word. Now, even though water is super important, wind still plays a pretty significant role in deserts, though. Now, wind can carry sediment just like rivers do. It transports it. So wind carries fine sediment like dust as suspended load. So when there's a big dust storm, it's all really fine-grained clay, maybe silt-sized pieces. There's a couple lovely examples here. On the left is a haboob. This one, I believe, was in either Iraq or Afghanistan. It's a military installation there that the picture was taken at. On the right is actually dust that's blowing off the Sahara and crossing the Mediterranean Ocean. So that's suspended load, but it also can carry stuff as bed load. Larger sediment rolls and bounces along the ground in a process called saltation. And this is what happens in your sand-sized pieces. So your sand-sized sediment gets carried as bed load. Now, if you'll remember, in rivers, gravels do get carried in rivers as bed load. But good news, we don't have many winds that are powerful enough to carry gravel as bed load around here, which is a good thing. And what's interesting is because of this process of wind blowing fine-grained dust and sand away, it forms a desert pavement. So this is where coarse sediment that's too large to be eroded by the wind is left behind. And so all the smaller stuff gets carried off. Let me show you a little picture real quick. There you go. So you end up with a nice mix of a bunch of different sizes, but as the dust and the sand gets blown away, you just get those big things left behind. And that big thing left behind is called a lag deposit. And that actually tends to protect the finer grain stuff under it. But that's what this ends up looking like. Because that lag deposit sometimes will form a desert pavement. And this looks like either like a mosaic tiles or sometimes like cobblestones covering the ground. And this is one of the reasons why deserts tend to be really rocky versus really sandy. Now, wind-blown sediment only gets about waist high in height because of mechanics and physics there. And so wind-blown sand starts to act like a sandblaster, and it can cause erosion of the rocks within the landscape. The remnant of the rock behind, after it's been basically sandblasted, is called a yardang. And these are often either mushroom-shaped, like you see in the picture here, or they make elongate ridges. Now, this mushroom shape is interesting. It's kind of a two-fer process. One thing is a lot of times you have softer, more erodible material on the bottom, but that's about as high as that wind gets blown too. So it kind of tells you how high the wind is. Another kind of interesting wind erosion remnant is called a ventifact. And so a ventifact is a faceted rock. And faceted just means it's got lots of surfaces. When you cut a gemstone with all the little flat faces, that's called faceting. And this is, again, because of the erosional power of sand. So you can see in the two little time periods here, you have wind all coming from one direction, so it's wearing down your rock into a nice kind of flat surface. And then the wind changes, the rock moves, and now a different side is getting eroded. And this happens a few times. You get these really neat kind of pyramid-shaped rocks like this, or like that. This one's on Mars. Mars is well known for its dust storms and its wind storms that blow up. Now, it's got a lot thinner atmosphere than we do here on Earth, but it's still enough to start blowing things around, which is actually pretty cool. Now, wind doesn't just erode, it can also deposit. And obviously, our most common deposit is a sand dune. So this is made obviously of sand. So we've got that saltating sand that's being carried as bed load. And you can tell which way the wind is blowing in a sand dune because the sand dune always has one side that's more steep than the other. If you see in the little diagram here, the left side is a little more gentle and the right side is a little more steep. So what happens is the wind blows up that gentle side, and then your little sand grains hop all the way up there. When they get to the very top, to the crest, they slide down that steep part. That's called the slip face. And you can see if you get like a lot of those slip faces, those are actually saved as layers, and that's what makes cross beds. And we've looked at cross beds when we did sedimentary rocks, and so that's how these are actually created. So we could always tell which direction the wind was blowing by looking at the steepness of the edges of the sand dune. Here's an example of some cross beds. It's one of my favorites, the Navajo sandstone up in northern Arizona and Utah. And they're highlighted in red, so you can see that in this case, the wind was actually blowing from the right side of the screen across to the left. I'm going to look at a few types of sand dunes really quickly, just because they're kind of interesting. The presence of sand dunes, even just having a sand dune in the first place, because a lot of deserts do not actually have them. The presence and the shape of the sand dunes depends on the character of the wind and the sand supply available in the area. So an area that has a really big supply of sand and has lots and lots of dunes is called an erg, an E-R-G, or a sand sea. Erg, I believe, is Arabic in nature as well. Just because, like I said, we have a lot of Arabic terms in our desert and stuff. So let's look at what kind of sand dunes you can form. So the first type is called a barken dune. These form when your sand is fairly scarce, so they make these little crescent-shaped dunes all by themselves. You need wind that blows steadily from one direction, and the tips of the crescent point downwind. So you can see it shows up really nice in this image from Mars. These are sometimes called the fortune cookie dunes on Mars. So in this case, the wind is blowing from the top left to the bottom right part of the screen, because it's blowing across that kind of gentle slope of the outside of the fortune cookie, blowing up that direction, then across that steep face. A star dune is one of my favorites, and I think this is kind of the picture we often have of dunes. These form where the wind shifts directions a lot. So you have wind that comes from lots of different directions. And in this case, you have crescents like barken dunes, but that end up overlapping and pointing different directions. So sometimes you just have to look for those steeper faces, but they may have a number of them. And this is an example of a star dune from Namibia. We also have transverse dunes. These occur where you have lots of sand. You need enough sand to bury the ground surface completely, but just moderate winds. You don't want a lot of wind, just moderate ones to blow it into these little ridges. And the crest of the ridges lie perpendicular to the wind directions. You can see in the diagram, the wind's blowing one way, but the line of the crest is going the other. We also have parabolic dunes. Parabolic dunes occur where you have the ends that point to the upward direction. So they look a lot like barken dunes because they're U-shaped still, but if you look at where that gentle slope is, in this case, the gentle slope is inside the U, so the wind's coming from the other direction. This is often found along shorelines. And sometimes what happens is you have a little bit of vegetation on the pointy ends that sort of anchor them, and everything forms behind it. I couldn't find a really good photo though. These are not great photogenic sand dunes, sadly enough. Our last type is the longitudinal dunes. This happens where you get abundant sand and steady, strong wind. In this case, you've got ridges, but these ridges are parallel to the wind direction. In a lot of cases, you could tell because they're symmetrical. And in the picture, I'm not sure where it's from, but the longitudinal dunes are on top of bigger dunes, so that's actually not that uncommon. So what we've seen is how and where deserts form. We've looked at some examples. We also looked at erosional and depositional features found in deserts.